in the nearest neighborhood, and you will tell us about fermions of different masses.
Panie profesorze, chyba po polsku można.
Będziemy głosować? Ktoś nie rozumie.
Tak, może być po polsku.
Jak kto nie rozumie, się
Jak na pierwszym posiedzeniu Polskiego Sztabu Generalnego, jak marszałek Rokosowski został z marszałka rosyjskiego, został marszałkiem. Marszał, my chwilę Polaki, można говорить по-русски.
Fermionach, ultrazimnych fermionach w różnej masie i układy, o których będę mówił, to będą układy jednowymiarowe i z punktu widzenia teoretycznego układy jednowymiarowe są o tyle ciekawe, że zachowują się bardzo często w sposób zupełnie różny od podobnych układów, które są w trzech wymiarach.
Które są ciekawsze, bo są bardzo proste.
Tak, z jednej strony są proste, z drugiej strony mają na przykład w przypadku oddziałującego gazu sfer i sztywnych pól, to w trzech wymiarach sytuacja wygląda zupełnie inaczej niż w jednym wymiarze, ponieważ one nie mogą się zamienić miejscami, więc to są takie tego typu własności i też gęstości stanów inaczej wyglądają itd., więc z jednej strony są prostsze, ale z drugiej strony też mogą coś nowego nam powiedzieć. Więc motywacją teoretyczną właśnie jest to, że te układy jednowymiarowe są bardzo ciekawe. Z drugiej strony eksperymenty na ultrazimnych gazach pozwoliły wyprodukować taki układ doświadczalny, w którym został zrobiony gaz Środowe, właśnie taki gaz sztywnych kul, więc to zawsze dla teoretyka jest miłe, jeżeli to co jest...
Ale czy rzeczywiście to jest takie ciasne, że one się nie mogą minąć?
No.
To wątpię.
Aż tak to nie, ale to jest bardzo dobrze modeluje te rzeczy, zaraz do tego wrócę. I oczywiście
atomy są jednak rozmiarów atomowych, a ta pułapka...
Ale to co istotne, to jest zasięg oddziaływania ich, to znaczy ta stała zwana długością rozpraszaną.
za chwilkę do tego
Pytanie jest o jeden wymiar.
jeszcze kolejna rzecz to jest to kilka atomów. To tutaj z kolei bardzo ciekawe jest przejście właśnie tych kilku atomów do układów wieluciałowych. Jak to przejście następuje, ponieważ te układy też inaczej wyglądają, te oddziaływania wielociałowe, inaczej to przejście jest ciekawe. I tak jak powiedziałem, eksperymenty, które są od kilku dekad prowadzone na ultrazimnych atomach, więc pułapkowanie i chłodzenie atomów jest dosyć dobrze opanowane i na takiej chmurze zimnych atomów można na to nałożyć sieć optyczną, czyli sieć takich wzajemnie prostopadłych pól laserowych, które tworzą fale stojące. I teraz w węzłach lub w strzałkach takiej sieci optycznej te atomy będą przyciągane. I teraz w każdym wymiarze możemy, dosyć dobrze eksperymentatorzy potrafią zmieniać rozmiary, w jakiej spułapkowane są cząstki. I w szczególności jeden z tych wymiarów można ścisnąć, tworząc takie płaskie dyski, efektywnie dwuwymiarowe, lub jeżeli zrobimy takie ściśnięcie w dwóch wymiarach, to wtedy i cały czas pamiętamy, że to jest bardzo zimny gaz, to w tych wymiarach poprzecznych atomy są w stanie podstawowym, natomiast w tym wymiarze podłużnym to jest po prostu, jak każde minimum potencjału można opisać w pierwszym przybliżeniu za pomocą oscylatora harmonicznego i akurat w tych doświadczeniach, jak sobie te sieci są dosyć głębokie, więc ten opis jest bardzo dobry. Także ta jednowymiarowość jest w dużym przybliżeniu spełniona. opisywać to faktycznie modelem jednowymiarowym. Więc jeśli chodzi o ten gaz, ultrazimny, który znajduje się w tej pułapce, takie atomy składają się z neutronów, protonów i elektronów. I teraz w zależności od tego, czy liczba czy suma tych wszystkich cząstek jest parzysta czy nieparzysta, efektywnie możemy mieć do czynienia z fermionami lub z bozonami, jeżeli dostatecznie dobrze schłodzimy ten gaz. I
nawet jak nie schłodzimy, to mamy do czynienia z bozonami lub fermionami, tylko to jest nieistotne.
tak. Ale jednak, żeby badać i widzieć te własności, to dobrze schłodzić.
Daniel, you should switch to English.
Okay. Okay, so if we have, so I will focus on fermions because this is the subject of my research, and in fermion system experiments, there is the total angular momentum is integer and is half integer, and one can choose two projections on the total momentum that won't change one into another in an experiment, because to change from one to the other projection, you would have to change the spin of the nucleus, and in these ultra-cold gases, the collisions don't change the spin of the nucleus. So if we if in experiment some atoms of one projection are produced and another number of the other projection, we can call them spin up and spin down. They're polarized, and so in fact we can have two types of fermions of different flavors.
But you are talking about the spin of the nucleus, but the spin of the electrons is probably
Yes,
more important because the magnetic moment is much
Sure.
stronger.
of course.
Yes, because I didn't understand the question.
Well, I questioning that the spin and the magnetic moment of the nucleus is
It's of
of
any
greatest
relevance.
importance because it's 2,000 smaller, about 2,000 smaller than the magnetic moment of the electron.
The message is that the spin of the nucleus is also important because you want to create two species of fermions which are distinguishable. And if you have a spin of the nucleus, for example, 1/2, like in lithium atom, and the total angular momentum, electronic angular momentum is also 1/2, sorry, nucleus is 1 and electronic is 1/2. Then you have two kinds of lithium atoms, one with total angular momentum 3/2 and the second 1/2, the total angular momentum. And it means that these two kinds of fermions are completely distinguishable from the point of view of experiment because during collisions the spin of nucleus cannot be changed. And this is all, but of course spin of electronic part is important part of interaction.
And the magnetic interactions do play a role, but not so much for lithium, for instance. So indeed, for the dipole-dipole forces, it's only electronic clouds.
Yeah, that's what I meant.
So you have two kinds of lithium atoms, one with total angular momentum 3/2 and the second
Yes.
one with 1/2. So they are completely distinguishable.
They're distinguishable, and within one flavor there is of course a Pauli exclusion principle, and one can use this Pauli exclusion principle. So one atom per one state. When we change the potential of a trap, we can tunnel out the redundant fermions, and in this way, this group in Heidelberg can produce in a trap setup when in every such potential there are n up number of spin up fermions and n down numbers of spin down, and they are fixed.
So in addition to the laser field, you also have a static magnetic field.
Of course. They are magnetized.
Yes.
Yeah, you have also the magnetic field here.
Yes. She said they are polarized.
And apart from the number of particles and from the shape of the trap, the dimensionality, one can also use flashback resonances to control very precisely the interaction between two atoms. Because there's usually an external field, very widely it is a magnetic field used in experiments, which can tune the interaction from attractive to repulsive. They can also not interact at all. So this is another control parameter that experimentalists can do. And there's, for example, an experiment when one fermion down polarized is in a trap, and then one by one the other flavor is added to reach the limit impurity in a fermi-sea of a different flavor. So those are the experiments that are already done in the laboratories, and this is those experiments are on lithium-6, and there are also another set of experiments that use mixtures of lithium and potassium. They right now they cannot do the few fermion experiments, but still I think these experiments are the development is going so fast that it seems that at some point they probably would manipulate with fermions of different masses. And so back to the theory. This is a Hamiltonian. This is my Hamiltonian, and as I said, it is one-dimensional. So those are the particles down polarized with a mass m down, trapped in a harmonic oscillator with a frequency omega. Here is a part kinetic and potential for an up particles with the same frequency omega and
which is not particularly realistic. That both frequencies are identical.
For the same mass or for
No, for different masses.
yes, the ratio between as far as I know, the ratio between frequencies in lithium potassium is 1.5 or something, and this model is much simpler when I put the same omega, but we checked it also for the ratio, the experimental ratio, and the results are the same. I maybe comment on that later. Yes, and the mass which could be different and up, and the particles of two different flavors interact via this delta potential, which this is a really good model for the things that are happening in experiment, and this is the effective one-dimensional interaction, which is tuned, for example, with magnetic field. And so this Hamiltonian is very general with many parameters. For example, there's when an up and n down is equal to 1, it was work of Professor Jean-Jacques and Bush and Williams that they showed that they analytically solved such equation. And and the solution for t equal to 0, the solution is known from the course of quantum mechanics. There are Hermann polynomials multiplied by Gaussians, and what is important, those wave functions contains the mass of a particle which they describe, and energies are linear with a quantum number, and doesn't depend on mass. So we can see that h bar omega is the only energy scale in this problem. When we solve on the single particle level the eigenstates for
That's without interaction.
yes, this is without interaction. This is
harmonic.
yeah, this is harmonic oscillator. But if we compare two different particles of two different mass trapped in the harmonic oscillator with the same frequency, we can see that here I use the ratio between those two masses. We can see that for equal masses the wave function is broader, and when we put here I would use alpha equal 40/6, which is for potassium lithium mixture. We can see that this wave function is
This is the wave function of what?
This is a wave function of ground state of a harmonic oscillator of one particle.
For heavier particle.
For heavier particle.
So there's no alpha if there's one particle.
But
What does alpha mean if there is one particle?
this is compared to the
One
unit
of each kind.
particle of unit mass. For example, this is a lithium atom.
Of course, if you increase mass, then the exponent becomes.
course, that's
Yes,
what
yes,
he says.
yes.
To jest, nie ma żadnych
I don't say that it's very new or just a simple
It's not
fact.
very.
But important remark for
Yeah.
further analysis.
And, we also know from similar studies of mixture of two different masses in uniform potential that mass difference leads to separation in a system in uniform potential. Here we have a harmonic oscillator. And it's convenient to use unitless masses, dimensionless units, and as I said before, the only energy scale is h bar omega.
So there is no interaction between particles of the same mass.
Which
Yes,
is realistic.
which is
Because
very
they are
realistic because those are
Because
fermions.
they are
Very
so
cold.
So there are no in S-wave approximation they cannot
To tylko kontaktowe.
yeah.
and to build a unit of distance I have to put a unit of mass, so I chosen it to m down, and this is the unit of distance, and all other possible units I can build from mass and energy and Planck constant. So because I know that what is happening without interaction, I will expand this Hamiltonian. I will rewrite it to second quantization form, and the field operator will. As a field operator, I will use the basis for non-interacting fermions. That is the Hermit polynomial, this quantum oscillator eigenstates. So this is the Hamiltonian, and the main procedure is that I have to fix the number of particles. Then I also put the mass ratio and interaction. And in my method, I compute all of the matrix elements of the full many-body Hamiltonian. And then I perform exact diagonalization of the Hamiltonian. And as an output, I get eigenenergies and eigenstates of this Hamiltonian. And from those things, I can calculate observables. For example, single particle density, which I come to that later. Or higher order correlations, occupations number, time evolution, all the things that can be observed in experiments, for example. And it is worth to notice that the numerical complexity of this method is rather tough, because for only 10 single particle states, for a system of 5 plus 5 fermions, and there are over 60,000 many-body states, it will give a Hamiltonian with 4 billion matrix elements, and only few of them are non-zero. It's yes, it's 10,000 smaller than the full matrix. It's of course we would like it to be even smaller, but it is how it is. So
How many single particle states do you have? 10 states, okay.
Yes.
Not 10, but 10.
Which is for 5 plus 5 is maybe not in strong. It would be okay for weak interaction, but for strong interaction, 10 maybe to
Maybe insufficient.
Yeah. And so I fixed the number of particles for 3 heavy and one of the other flavor. And here you can see the spectra with respect to interaction for this Hamiltonian, for equal mass case and for unequal mass case. And this is already well known from the literature. And what can we see that for the zero interaction we have the harmonic oscillator levels, and in a strong interaction we have the degeneracy, quasi-degeneracy, and such manifolds do form. And what does it mean, strong interaction? This strong interaction limit, for example, in here, I would say is, for example, 10 is already a strong interaction, because in non-interacting, the spacing is h bar omega, so 1 in this plot, and here this is much smaller than this energy on the non-interacting system. Now, if we compare this plot with the equal mass,
And can one say that say coupling strength equal 10 means that interaction energy is about 10 times larger than the
Yes.
spacing between the
Yes.
atoms?
and here you can see that this we have also quasi-degeneracy, but it is the degeneracy is lifted, as we can see here, for example, and mass ratio, and this lifting of degeneracy can be already seen in the level of Hamiltonian, because if the masses are the same, there is an additional symmetry. We can change mass, those particles spin up to spin down, and nothing happens. It doesn't matter if we have 3 particles up and 1 down, or 1 up and 3 down. But if we have an mass that is not equal, the degeneracy is violated, and the degeneracy is lifted. And there are some works that consider the systems with mass ratio unequal to 1 for a specific number of particles, as for example this Danish group here. But this method is very general. I can pick any particle numbers I want, unless I have a computer big enough. So another
So już to były 20 lat temu przez nas zrobione.
so now so that was the spectrum, so which was different after changing the mass of one type of particles. So we can suppose that on the other observables would also be changed. And here we have a single particle density defined on a ground system, ground state defined as this. The single particle density sum up to the number of particles, of course, and those results were the results of the Danish group that were already known, and they find out that when they in a strong interaction limit, the majority of the particles will split from such spin domains. And we checked what is happening when there is a mass imbalance in the system, and for almost not interacting system, we can see that there is a big difference. But if we think about it closer and get this, use this scaling with mass property of wave function, we can see that those two pictures would be the same if we scale this. So it's, one can say this is nothing new apart from the localization of the heavy particles, which is nothing very new. But if we increase the interaction between those two components, we can see that the one particle starts to split, and in strong interaction it stays like as this. So we have the exactly opposite situation as in the case of equal masses. And so the question is if here always, because in this work always the majority of particles split up to, I don't remember, 9 or even more particles, and the impurity was in the middle. In our case, impurity splits. So the question is if always impurity will split, or maybe this is because these particles are lighter. And always lighter particle will split, and heavy will be in the middle. So we check that for different alpha ratios, and this one is important because those you have already seen on previous slide. Here is alpha smaller than 1, so the blue line are the lighter particles. So it means that always lighter particles will separate, and we did that for...
I don't understand what's the rationale in studying separately alpha smaller than 1 and larger than 1. They are identical situations.
No, one of them is free.
There are no equal amount of species.
Ah, 3 to 1. Sorry. Sorry.
And here we calculated everything for a different number, different configuration, different number of particles. And so here we have this 2+1 situation. Everywhere red line corresponds to the light particle and blue for heavy. And everywhere heavy particles are in the middle and light go outside. Here we have 3 heavy, 3 light particles, and even the symmetric case, which for equal masses the profiles should be the same, exactly the same. Here we have the symmetry is violated, and lighter go outside. And we did that, it holds from just 2 particles. We check that up to 10 particles that this is always true.
So the heavy ones have a lighter trap, right? And a stronger trap.
No.
So that's
No, omega is the same for both.
Energy.
no, but alpha becomes a multiplying factor for the heavy
No,
ones.
what you are saying is that, of course, the
No.
width of the ground state is different, but that has been pointed out already.
In this problem,
But that's the
there are
reason
2
that-
parameters.
Sure.
There is contact energy, which depends on the spreading, and this depends on the masses, if it is broad
Yes.
or narrow wave function. And the second is single particle excitation,
Yeah.
and so there is it might be in principle a competition in the system if they prefer to go up or to separate.
But separation means go up.
Yeah, yes. But now he started the case when single particle excitation is the same, both for independent on the mass. Heavy or light particle is the same energy, which is
Right, because the others.
So I would say that from the single particle point of view, the separation, energy cost for separation for both species is the same. Because single particle excitation energy is the same. So the only
But
reason
the wave
of-
functions are different, I guess.
yes, but
Yes.
it comes from the interaction,
from interaction. Only
not from single
from
particle
single particle,
excitation.
because in principle it might be competition. Single particle excitation or interaction. No,
No, it's not clear to me, but I'm not going to hold things up. So.
Okay, so this was for the ground state, and then we wonder what is happening with the ground state. There are some imperfections in producing ground state, strongly interacting ground state, and then we model a mixed state with a thermal-like state with this Boltzmann weight, and so we have a density matrix, and we can calculate all the observables as for the ground state. And here we can see the first row is alpha equal to 1. Here we have lithium potassium mixture. Also 3 + 1 system as before with strong interaction. Here this factor, I wouldn't call it temperature because it makes no sense, but this parameter of mixing. So if it's 0, we have the ground state, and when we increase it just a little bit for equal mass case, those domains would disappear, and we eventually we have a Boltzmann like distribution. But for different mass case, when we increase this parameter of interaction of imperfection, of impurity, we see that the separation remains. Only some details of density disappear, and this holds for parameters that are when there is no separation at all for equal mass case. So we think that this mu kind.
Why don't you resist calling T the temperature? After all, this
On four particles.
gas has some temperature.
But
Sure.
I don't know because the thermalization in 1D for those particles may be.
Oh,
No, it doesn't matter.
What you are saying is that it's hard to produce such a state in the lab,
Yes.
but once you wrote it, it's here.
Yeah, good.
But the idea was to check what is the role of imperfection in preparation of the state.
for example,
Yes.
temperature.
And then for
Yes,
example,
and this is
let's
some parameter which controls the mixing between eigenstates.
But it's a temperature
Yes.
state
From
of the
this point,
system.
this is the
It's not a
temperature
question
state.
whether
Yes.
If you have such distribution
sure.
of
Yes, if it's
Of
true that
inflation,
this is the
it's called thermal.
system that
Yes,
is
of
produced,
course.
Yeah.
the state that is produced. So this seems robust to the
Yeah.
imperfections, and hopefully maybe observed someday. And in this problem, it was very important that there was only one energy scale, H bar omega, and 2 length scales, because the heavier particles were more localized. And then now we can think what would happen if we change that to the opposite situation, when there is only one length scale and the energy is somehow mass dependent, and such situation is in box potential, when the length of the box called L here is the same, and the wave functions as you can see here does not depend on the mass, but the energies do. They're not here. They're quadratic in the quantum number and inversely proportional to mass. And so the model is basically the same. The only difference is here that we have a Bob potential. Here is a flat potential with infinite walls. What we did was, the procedure is completely the same, the second quantization, Hamiltonian, and so on. And such potentials are not only the theoretical wish to be, but they were already produced 3 years ago in Cambridge in Harry-Babbitt group. And so what we get from this box potential, those are the spectra, and here I have an interaction and some energy. The units are not there's some complication with units, but the only important thing is that those units are the same, and you can see that in the equal mass case in box, there are also degeneracies, which are lifted when the masses are different. The argument for breaking violating this symmetry still holds here in this potential, and because in heavy particles case, this mass dependence is that the gaps between energy levels for heavier particles are smaller. We can see that here these levels are very close to each other, and also the scales are different. So this is how the spectra look differently from the quantum oscillator case. And when we see on the densities of such system, we can see that we can also see a separation here, but this time the blue line, which is the heavier particles, to separate, and it does not depend on the number of particles. So
now it does not cost at all to push some particle to a side. Yes. Before it was going up in the potential.
Yes.
Because
Because
before it was more costly to push
Sure.
the heavy ones
Yeah.
further out. That's why the
Absolutely.
light ones were there. Even though the energies levels were the same.
so now I think
Now, of course, squeezing something costs increasing kinetic energy.
yes. And returning to this question about the that in real experiments we have not the same frequencies. If we do the calculations, this 1.5 energy, this if we change the frequency of one particle, we are somehow in between those two, the box potential and harmonic potential, and for this ratio 1.5 from the experiment, there is no big difference from the slides for harmonic oscillator as I showed you before, because here you can see that this is really an order of magnitude of difference, and there is the difference slide. So that's it. Thank you for your attention.
It would seem that for a large number of particles, some kind of a mean field approach would be appropriate, or density function. Has this been tried?
No.
Yes.
No, not by us.
By us,
Professor Brzezinski says yes.
in fact, in 3D.
In the non-interesting case of mass degeneracy and large positive coupling, it seems that this delta potential seems to discourage the two species to be at the same place, right? Can then this degeneracy be understood as a just consequence of Pauli principle? I mean, you have those fermions become quasi-identical.
Yeah. Yes.
No, but there is also because there are some kind of we have some kind of fermionization of this distinguishable species, yes. But the fermionization does not mean that they have to be antisymmetric at the relative wave function. And this quasi-degeneracy comes from the fact that you can assume a full antisymmetrization, full symmetrization between species, or some intermediate states. And the number of this degeneracy level comes from this combinatorical factor of possible symmetrizations.
One of possible state is modulus of this.
Yes, this is full symmetrization.
This is fully symmetric with zero.
Yes.
looks exactly. Density
Takie
is
doświadczenie
exactly.
jest bardzo małą liczbą.
Są takie
I
doświadczenia.
have
No ale to co...
I have question. You've been
Okay.
showing that at some, when the masses were identical, it was preferable for minimum of energy to have heavy particles in the center. But then when you went to the different masses and different excitations energy, you got opposite situation. Is there any phase transition between having this heavy particle in the center and when you are going to this, I don't know, box-like potential or something, that out of a sudden this heavy particle goes to the sides?
Yes, in fact, this is the ongoing project that we have. Because in this case, there is the experiment is that they trap the atoms and then they add to that the walls and then they slowly decrease this potential to flat situation, and this is the potential we have modeled, and there and we can see that there is a point when the heavy go outside and the light particles go inside, and
But is it of the second order type, or is it smooth going through situation where they occupy about the same region? Do they switch all of a sudden, or
yes, they
do
switch.
go
Yes, this is
smoothly?
yes, they switch.
So it's like a first order.
Yes.